In this lesson, we're going to multiply complex numbers that are in polar form, and we're going to derive a formula to do that. And what you'll see, in most cases, it's easier to multiply complex numbers when they are in polar form than as opposed to rectangular form. So recall that the polar form has the modulus, and then inside here times the cosine of the argument plus I times the sine of the argument. So we'll start off with two complex numbers, and we're going to do the generic case. So our first complex number is represented by z1, and that's r1 times cosine of theta 1 plus I sine of theta 1. And then z2 is r2 times cosine of theta 2 plus I sine of theta 2. And what we want to find is z1 times z2. And what that would look like is r1 times all of this and then I multiply that by r2 and the cosine of theta 2 plus I times the sine of theta 2. Okay, so when we multiply, we're going to multiply these coefficients, so we'll regroup them, and then we're going to multiply the binomials. So let me regroup r1, r2, and we end up with two binomials that we have to multiply together. So here's that one, and here's this one. So when we do this, when we multiply these binomials, remember the I is going to be in there, so when we multiply a term where we're squaring the I, the imaginary number, that's going to end up being -1. So we're going to go through that and see what we come up with. Alright, so throughout this process, the R1 and R2 are just going to be hanging out here in the front. And again, we've got to multiply this whole thing out. So we do cosine theta 1, cosine theta 2, so R1, R2, and then in parentheses, cosine of theta 1, cosine of theta 2, and then we have cosine of theta 1 times I sine of theta 2. So we put the I first, and we say cosine theta 1, sine of theta 2, then we have I cosine of theta 2, sine of theta 1. Or we can say sine of theta 1, cosine of theta 2. And then finally, we have I sine of theta 1 times I sine of theta 2, which means the i's turn into a -1. So it's negative sine of theta 1, sine of theta 2. So now what we do is that we regroup. We group our real terms together and our imaginary terms together. So here's what this thing looks like. We still have our R1, R2 out in front. And then our real terms are cosine of theta 1, cosine of theta 2, minus sine of theta 1, sine of theta 2. That should look familiar. Plus, down here, I have the imaginary part, which ends up being sine theta 1, cosine of theta 2, plus cosine of theta 1, sine of theta 2. And again, these two things should look familiar. This one is the angle sum identity for cosine, and this one is the angle sum identity for sine. So I can replace this part. Hold up. I can replace this part with the cosine of theta 1 plus theta 2, and I can replace this part with the sine of theta 1 plus theta 2. So we have a way to represent the product of two complex numbers in polar form, and here it is. You say it's going to be R1 times R2, and then all that's multiplied the cosine of theta 1 plus theta 2 plus I times the sine of theta 1 plus theta 2. So when you want to multiply complex numbers in polar form, you do two things. You're going to multiply the moduli, which means the radius is here, r1 times r2. And you're going to add the arguments. And then you'll leave them in this form here, where you'll have a single number out here. You'll have a cosine of an angle plus I times sine of an angle. So we're going to work through an example to show you how to do this. All right, here we go. We have z1 is 8 times cosine of 3 pi over 4 plus I sine of 3 pi over 4, and z2 is 2 times cosine of 5 pi over 4 times sine of 5 pi over 4. I don't know why that 4 is missing, so we got to put him in there. Now, a couple things. You have to have the same angle here, and the same angle here. But these two don't have to be the same. So if I want to find z1, z2, I find r1 times r2, and that's going to be 8 times 2. So multiplying the moduli gives me 16, and then I have to find theta 1 plus theta 2. That's going to be 3 pi over 4 plus 5 pi over 4. Sometimes we have to get common denominators. We always want to reduce our fraction down with whatever we get. When I add those two together, I get 8 pi over 4, which means adding the moduli gives me 2 pi. So my final answer, z1 times z2, is going to be 16 times the cosine of 2 pi plus I times the sine of 2 pi. And that's my answer. Now, if I wanted to convert this to rectangular form, all I do is I evaluate the cosine of 2 pi and the sine of 2 pi, and then I would multiply by 16. Doing that, this is a quadrantial angle. So these answers are either going to be 0 or 1. For the cosine of 2 pi, it's 1. For the sine of 2 pi, it's 0. So multiplying those two complex numbers out, we end up with a value of 16, z1, z2. That's in rectangular form. So this is rectangular form, and this one is in polar form. We can represent it both ways. Sometimes you have to write it in polar form first. You're not given the value in polar form. So in this case, we're going to write these two complex numbers in polar form and then find their product using the rule we just derived. So z1 is a 5 plus 5i. If you think about that, when both real and imaginary are the same numbers as in the first quadrant, this is a 45-degree angle. In polar form, if you wanted to find the radius, it's going to be the square root of 25 plus 25, and that's going to be 5 radical 2. The angle is going to be pi over 4. Or you would use the inverse tangent to find it, but when they're both positive and they're both the same value, you know your angle is going to be pi over 4, which is 45 degrees. For the second one, I have z2 is just the value of 4. That means the imaginary part is 0. So if you were thinking about this, he's sitting over here on the real axis. And there's the imaginary part. So the radius, the second radius, there's the first radius, the second radius is 4, and this argument is going to be 0. So to multiply them together, I need r1 times r2. That is 5 radical 2 times 4, which is going to give you 20 radical 2. To add the arguments, it's pi over 4 plus 0, so he's just going to be pi over 4 in the end. So z1 times z2 in polar form is 20 radical 2 times the cosine of pi over 4 plus I times the sine of pi over 4. And that's how you do these problems when you start with a rectangular coordinate and convert to polar form. So if multiplying complex numbers in polar form consists of multiplying the moduli and adding the arguments, then dividing, finding the quotient of the two complex numbers, That means we're going to divide the moduli. And we're going to subtract the arguments. So it's a pretty easy formula to remember. So it's going to look like this. Z1 divided by Z2 would be R1 divided by R2, and then the cosine of theta 1 minus theta 2 plus I times the sine of theta 1 minus theta 2. So it's just the opposite operations than with multiplication. Alright, so here's an example of how this works. I want to find the quotient of these two complex numbers that are in polar form. 2 cosine of pi over 6 plus I sine pi over 6 divided by cosine of pi over 3 plus I sine of pi over 3. So when you don't see the coefficient there, that's an implied 1. So I want to divide the moduli, R1 over R2. That's going to be 2 over 1. So that'll give us 2. And then theta 1 minus theta 2, that's going to be pi over 6 minus pi over 3. This is where it only gets slightly complicated. I need to convert this so I can subtract it from 6, which means I multiply top and bottom by 2. And that's pi over 6 minus 2 pi over 6. So that's going to give me negative pi over 6. We could just leave it like that. So in the end, the quotient, the final answer is going to be 2 times the cosine of negative pi over 6 plus I times the sine of negative pi over 6. And that's the answer in polar form, and we'll look at what it would be if we converted to rectangular form. We will talk about that in class.